Thanks very much for that great introduction. I'm not only the director of the Swinburne Data Science Institute, but also AusGrav, the ARC Centre of Excellence for Gravitational Wave Discovery. And a lot of the work we do is in pure science. I'm going to use a special presentation tool that we use for public outreach to give you a flavour of what we do. So gravity was really the manifestation of four breakthroughs, one by Galileo, one by Kepler, Isaac Newton, and Albert Einstein. Galileo changed our view of the universe forever when he took the first telescope and pointed it at the first telescope he had access to, and pointed it at Jupiter. And he noticed that Jupiter had moons, and that the moons traveled around Jupiter in an interesting pattern, with the inner moons traveling faster than the outer moons. And he realized that if Jupiter had moons and the Earth had a moon, but the sun didn't have a moon, maybe it was the sun that was at the center of our universe, if you like, or solar system, and not the Earth. So this was an important breakthrough. Kepler realized that there was a geometrical relation between how the planets moved around the sun and the length of time that they took to travel through parts of their orbits. And he thought that God was using mathematics to explain the universe. He was kind of right in a way. And Isaac Newton showed that his universal law of gravitation and his three laws of motion actually led to the derivation of Kepler's laws. But it wasn't until Einstein came along that he realized that if gravity worked in the same way as electromagnetism, any two objects in the universe should radiate invisible gravitational radiation. But he thought the amplitude of the gravitational waves was so small that they would never have any meaningful impact on any matter. He also realized that if black holes existed, they would give off gravitational waves at a very high rate if ever they came into close proximity of each other, and that they would soon radiate all their orbital energy in the form of gravitational waves. So 100 years after these postulates, scientists actually built enormous laser beam related detectors in the US, fired a laser beam down two 4-kilometer long tunnels, and managed to see the mirrors wobbling, if you like, with a particular pattern, which indicated that two black holes about 1 billion light years away in the universe had merged, and gravitational waves were discovered. And my Centre of Excellence tries to detect these gravitational waves on a routine basis. So we're all familiar with the Earth. It's 40,000 kilometers in circumference. And Einstein was only aware of things like the Earth and the Sun when he developed his theory. Jupiter is a lot bigger than the Earth, and bigger still is the Sun. In fact, you could fit 1 million Earths inside the Sun. It turns out in the universe there are much bigger stars than the Sun, and this is a blue supergiant. And at the core of these stars, the pressure gets so high towards the end of these stars' life that the protons and electrons can no longer ignore each other, or can no longer repel each other, and they get compressed together to form a neutron star. And neutron stars are incredibly compact and have a gravitational force that is much, much greater than that of the Earth. In fact, over 100 million times the gravitational field. So telescopes like this one, this is the Parkes Radio Telescope, not to scale, is 64 meters across, and my group uses this telescope about 1/4 of the time to look through the universe to discover neutron stars. So neutron stars look a little bit like this. They're only 10 kilometers in radius, but they weigh 500,000 times as much as the sun. And they rotate. The slowest one rotates about every 20 minutes, but the fastest one actually rotates 700 times a second. So it does a complete revolution 700 times a second. And when the beam of radiation passes the radio telescope, we actually need to invoke data science to be able to process it. We have to capture over 1 billion samples a second and process it on an inbuilt supercomputer at the observatory in order to process the data from these neutron stars. Some of the neutron stars actually live in pairs, and they travel around each other not every year or so like the Earth goes around the sun, but in fact they travel around each other every few hours. And they carve out these eccentric orbits, which are a little bit like the eccentric orbits of the planets going around the sun. Now, some of these systems are very face-on, others of them are very edge-on. And they're emitting these beams of radiation that travel throughout the universe. And my group discovers these systems. And what we've discovered is that when you monitor these neutron stars, after processing literally trillions of samples of information, you can actually show that the orbit of these neutron stars shrinks by about 3 millimeters every few hours, and that in a few 100 million years, these two neutron stars will actually get so close to each other, they'll tear each other apart and give off a burst of gravitational waves that we can detect using our laser beams at the LIGO interferometer in America. So onto the Data Science Institute. Because I designed the supercomputers at Swinburne and a lot of the processing, I volunteered during the pandemic to lead the Swinburne Data Science Institute. This is our own welcome to country, which in the interest of time I'll go past, but I did want to point out that we've engaged a local Wurundjeri artist, Judy Nicholson, to depict how she would visualize gravitational waves throughout the universe, and I'm quite fond of her artwork. So data-driven science is the norm in almost every field these days. And our Centre of Excellence monitors these pulsars in order to try and prove Einstein's laws of gravity. We also follow up the optical afterglows when the neutron stars merge using telescopes like the one on the right. The object on the left down here, I don't know if you can see my cursor, but this is where the James Bond style laser fits, and it fires down these 4-kilometer vacuum tubes and back. And if a gravitational wave passes through, we actually see the distance between the laser beam and the mirror changing by about 1/10,000th of the width of a proton, and we're able to detect that quite easily. So here is what we're looking at, these black holes in the universe. These are objects so dense that not even light can escape them, some 30 times more massive than the sun. And about once a week, two of these things merge in the universe, and we see our mirrors change their separation in this nice way. And this is our model of what's going on, and that enables us to determine the masses of the black holes and also how far away they are. So this was me appearing on the 7:30 report, describing the first detection of two neutron stars merging. So this is 1 million times the mass of the Earth merging together. And we actually saw the last 4,000 orbits of this system in just 2 minutes. And here's the gravitational wave and the frequency of it going up as the two neutron stars got closer and closer. And then 1.5 seconds after they merged, we got a burst of gamma rays striking the Earth. And this meant that the speed of gravity was the same as the speed of light, to about 1 part in 10 to the 15, I think it was. A remarkable scientific achievement. So how do we do all this? We use a supercomputer at Swinburne called OzStar. This was designed to work on gravitational waves. It has 230 P100 GPUs, about 4,000 CPU cores, so it's mainly a GPU machine. About 10 petabytes of disk space, especially designed to maximize I/O, and there's about 192 gigs of RAM per server. So this computer not only does gravitational waves, it does all of the data science at Swinburne. And we've developed an inference package which uses Bayesian statistics to infer what the properties of the gravitational waves are, in fact, to fit these models. And we've found that this package is very good at doing Bayesian inference on almost anything that you can write down with a formula. And this paper has over 200 citations. It was developed by the Monash Group. You'll be pleased to hear, Monash people. We also have had quite a bit of success at spinning off companies. So Liquid Instruments is an ANU-based company led by Dan Shattuck. Dan used to chair our research translation committee until he attracted too much money in investment capital, and now he's the full-time CEO of Liquid Instruments. And it takes a lot of the gravitational wave techniques and uses them for just monitoring general lab data after it's been converted from analog to digital. We've recently created another company, Fourier Space, to work on the square kilometre array, and we have a little research translation feeding scheme for our junior researchers. We do a lot of public education and outreach. We have a lot of cool VR tools, and we used to put them on people's faces when we could still touch people's faces, but we don't do that anymore. But I'm using the same tools here that have been showing you our pulsars and gravity and so on. And this package is actually adaptable to be used in many other regions of science and education. We have some institute leaders. The Data Science Institute is what they call a virtual institute. In other words, they don't give them any money, but we get volunteers who work in data science to work with people on multidisciplinary projects throughout the university. And we're quite highly ranked in computer science in the ARWU, as meaningful as any of these metrics are. So Kai Quinn does a lot of machine learning, Jinjin Chen on data curation, processing and data privacy, and Hardy works in supply chain management. So I might stop there and take any questions.